Hello and welcome to TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy to understand videos. My name is Ebby, lead tutor for Math and Political Science. In today's video, we will explore continuity. Let's get started. To understand continuity, let's first define it. For a function to be continuous at a point A, three things must be true. The limit as x approaches a from the left of the function must equal L, which is a y value. Second, the limit as x approaches a from the right of the same function must also equal the y value L. So on the first condition, the superscript on the a, that's a minus, is from the left, and on the second condition, the superscript on the a value is a positive, which means it's from the right. And remember, a is an x value. And lastly, the third condition, f of a equals L. That means that there must be a closed dot at the same y value that the limits approach. So let's examine this function that we see, and let's examine specifically the point A. So a equals 3, and we're going to check the left-hand limit. So limits are like trajectories. So the left-hand limit means you go to the leftmost side of the graph. So the leftmost side of the graph that we see pictured here starts here, and then we take a trajectory path all the way to the x value 3. So we're going to follow this graph until we hit the x value 3, which is right here. 3. So we follow the trajectory, and we don't worry exactly if there's a closed or open dot. We only worry about where it's actually going to. So we followed it, and that point is 7. So the limit as x approaches 3 from the left is 7. So let's check the right-hand side limit. So the right-hand side similarly works. We go to the rightmost side of the graph, and we follow that trajectory, and it goes to the same value, 7. So we know that these two things are the same value, the first and second condition, so we can say that the limit exists. So if the first two things equal the same value, then the limit exists. Now let's check to see if there's a closed dot at the same value. So to do that, we go exactly to the value. We don't follow a trajectory, we go simply to the value, and we assess, is there a closed dot? Well, there is a open dot at the value 7. Even though it's at the value 7, there's an open dot. So that means that it's undefined at the point 7, which ultimately means that the function is discontinuous. So it's discontinuous because not all three conditions were met. Specifically, the function is undefined. So now let's talk about the different types of discontinuities that we can see. The first kind is a hole. This is also called a removable discontinuity. And in holes, the limits exist, but there is a literal hole in the graph somewhere. So in this case, the left and the right hand limits approach the same value, which look to be about 2, but there is a hole at 2. So therefore the function overall is discontinuous. So the second kind is a jump discontinuity. So in this graph, there are multiple jump discontinuities. We'll look at, let's say 1, for example, the x value 1. So that will be the point in question that we'll be assessing. So let's look at the limits. So the left-hand limit starts here at x equals 0 and goes to 1. But the right-hand limit starts here and approaches 1 from that angle, or from that side. So you can see that the left-hand limit for x equals 1 is 0, but the right-hand limit is 1. So that means that the limit does not exist. And also, there's a closed dot. So there's a closed dot at the point 1, but the limits don't exist. So that means that all three conditions, just like a whole, were not satisfied. So in the whole, the third condition was not satisfied, the open dot condition, and in jump discontinuities, the limits conditions are not satisfied. And then lastly, we have infinite discontinuities as the third picture, and that occurs specifically in this graph at the point x equals -1. So as you can see, the left-hand limit of this graph, starting at the leftmost side of the graph, starts here and goes all the way down towards -infinity. And the right-hand limit, starting here, goes, first there's a hole actually there, and then it goes all the way to positive infinity. So both limits tend towards infinity. That's why this is called an infinite discontinuity. So that means that the first two conditions are not satisfied because the limit does not exist. And also, even the third condition, if we're talking about specifically the point x equals -1, is not satisfied as well, because in this specific view of the graph, there is no closed dot at x equals -1. And then also, we can also assess a hole in this third graph at x equals 1, where it says it's undefined. So we even have two different types of discontinuities on that third graph. So determining continuity, we want to know, are the following functions continuous? If not, which parts of the continuity definition is or are violated? So looking at the first equation, f of x equals 1 over x plus 2 when x is not equal to -2, and 3dx if x is equal to -2. So we're going to use this along with the definition of continuity, those three conditions that we defined earlier, to solve this problem. So remember that the first condition deals with the left-hand limit, and the second one deals with the right-hand limit, and lastly the third is the closed dot condition, where there needs to be a closed point. So this piecewise function is already set up in this way. If we look at x is not equal to -2, those can be numbers smaller than -2 or bigger than -2, typically as we see it. But when introducing limits, we are getting down to the granular or the infinitesimally close numbers to -2. So what does that mean? If we're dealing, so not equal to -2 encapsulates those first two parts of the definition. So if we're thinking about numbers that are the left-hand limit, so less than -2, well, we typically think of, okay, -3, -4, so on and so forth. But what about -2.00000001? Those are also numbers smaller than -2. And then also, on the other hand of it, what about numbers that are slightly bigger? -1.99999 repeating, right? Those are technically bigger or the right-hand side of negative 2. But when you introduce limits to those numbers are so close to negative 2 on either side that they are basically negative 2. So I say all that to say the practical way that we solve these kind of problems is simple in a way, because all we do is we look to see if there are the same number in multiple places, and if there are, we plug in that number into the functions on the left-hand side and see if they're the same number. And if they are the same number, then it's continuous. The entire piecewise function f of x is continuous. And if they're not the same number, then it's discontinuous. But the reasoning that I explained just now is the reasoning of why that seemingly simple thing, procedure, works, basically. So let's actually, knowing all of that, let's actually solve this. So like I said, you plug in those numbers. So plugging in that negative 2 into the first equation will give us 1 over 0, which is actually infinity. So remember that I said that the not equal to represents the left and the right hand side of the limit. So if this gives us infinity, we know that that does not exist. So automatically, we know that this entire function is discontinuous since the first two stipulations were violated, right? And so we can still plug in negative 2 to see if we'll get a number. So plugging in negative 2, 3 to the negative 2 gives us 1 over 9, which is a closed dot. There's going to be a closed dot when you graph it at 1 over 9. But since 1 over 9 clearly is not infinity, we know that the function overall f of x is discontinuous. So let's apply this principle to the second function h of x. So we see 2 multiple places, we see 3 in multiple places, and we see 4 in multiple places. So we will be plugging in 3 different values into the places that we see it. So let's first start off with positive 2. So starting on this left side, we plug in 2 in the places that we see it. So we will be plugging it into the first and the second equation. So plugging 2 into those equations, we get 0 for both of them, which is what we want. So if we get the same number when we plug in the input, moving over to the right side of the screen, we know that the function is continuous at that specific point. So 2 is at 2, it's continuous. So now let's do the same for 3. So plugging in 3 into the second and the third equations, we get two different numbers, negative 2 for the second and negative 1 for the third. That means that the function is discontinuous at x equals 3. And then so lastly, we see 4 in multiple places. So we plug that in into the third and the fourth equation, x minus 4 and e to the x. And clearly we can see that those two numbers are also discontinuous. Which are actually violated then? Well, we know that plugging in 2, we get that's a continuous part of the graph, so none are violated for x equals 2. But for x equals 3 and x equals 4, when we graph for specifically x equals 3, when we graph 4 minus 2x and x minus 4, we will see that the limits do not exist, and then therefore the first two stipulations or conditions are violated, and the same thing for graphing x minus 4 and e to the x. Those limits do not exist, so therefore the first two stipulations are violated as well, meaning that discontinuous at 3 and 4, and overall this function is discontinuous because it is not continuous everywhere. Thank you for watching TutorTube. I hope you enjoyed this video. Please subscribe to our channel for more exciting videos. Check out the links in the description below for more information about the Learning Center, and follow us on social media. See you next time.